On the one part, it's yeah. It's only one here. Oh. Actually, you should. Oh, that's fine. Okay, for variables. I saw that the section 1 and 2 homework, focal chapter 4 is close. Did you guys finish? Yes, sir. No? Okay. Let me read. What's another do? The one, really like. Yeah. I suppose you guys finished the chapter 3 homework, 3.3.3.1. Do you have any more questions? Thank you. Okay, so this was one of the using the joint distribution to find the covariance. Covariance is one of the number that you have to calculate correlation. The covariance equal to expectation of this. We should know how to know expectation of x times y minus the multiplication of the expectation. The question, we try to make it shorter, so expectation of x and expectation of y is already given. So all you have to do is find out expectation of x times y. So that way, what? You just calculated.
I had just calculated it and did not read the full question.
Yeah. Are you getting the same number?
Yeah, I got the same number.
The same expectation. Okay.
Have you opened the 4.2 homework yet?
I did.
Okay. So then we're going to open the weekend.
Yeah. Evaluation of time. think you finished the one on, I sent actual word.
The actual one, okay, so what's the
They would, yeah,
Okay.
they'll be added.
Gotcha. Thank you.
Chapter 4 also have the additional.
Okay,
I kind of combine them all in one homework grade so that I don't have to add one more homework grade. Okay, finished? Thank you. Good.
That's what times two, so 2 times. 2 times. Just. Right, the 2 1 gets 9.
Zero multiply anything is still zero, so the y equal to zero, we don't have to do it. That doesn't, that only leave like a few that's non-zero. So 1 times 2 times 0.04, 2 times 2 times 0.05, 2 times 3 times 0.15, and then 2 times 4 times 0.1. So only 4 of those non-zero numbers. If the probability equals zero or the value for zero in the calculation. So this is saying it's a summation, the x value times the y value, and then times the probability of x, y. So it's going to be 3 months. Then you have to add up all the combination of this summation has to be main summation. And of course you have to minus this total summation minus 2.85 times 1.
Can you pull up a picture of our picture sheet? I forgot mine at home.
Oh, yeah, okay.
It'll be like 10 years.
Did you attend online before? You, okay, it's okay. I can also give you the image of.
Yeah, the image, and then I can take a picture and then.
Yeah.
Thank you.
Right. We did actually.
That's so many.
My calendar, it's 1. That's your image.
so if I took the homework, can I see?
This is
Bless you.
So you do any of the proofs for the- Also, it's.
Yes, of
Okay.
course. Thank you.
It doesn't say, I was like, okay, at least they this is something, so. I didn't do it.
So the final answer is negative 0.15. Any questions? Okay. So do you have any homework question you want to talk about before we start? I think we went through most of it on 4.2. Right, the end of the class last time. Okay, 4.2, the main calculation is to be able to calculate correlation coefficient. The correlation coefficient is a special number that represented the relation between these two variables. Specifically, it's representing any possible linear relation between the two variables x and y. So if you have a joint distribution, which was fxy, you can use the joint distribution to calculate the covariance. Essentially, that's the definition for the covariance, but the computation of it can be calculated using the expectation of the multiplication minus the multiplication of the two expectation. So calculate covariance, if the two numbers are changing in the same direction, covariance will be positive. If the x and y are changing in opposite direction, both x and y should be positive variable. They are numbers. So if you subtract the mean and if they are both bigger than the mean at the same time, it will cause the multiplication to be positive and correlation will be positive. If this is higher than the mean, but that one is lower than the mean, the multiplication will be negative, right? It will cause the covariance to be negative, which means they're opposite direction. And then covariance itself is not enough to be able to quantitate the measure. So we take the covariance divided by standard deviation of both. That's the number that measure the correlation between two variables, variable x and y. So with that, we have a little bit of discussion on the calculation of covariance. That is, covariance can be calculated by summation of expectation multiplication minus multiplication of expectation. And because of that equation, we realize the expectation of x times y equal to the summation of these two, right? Equal to the mean for x times mean for y plus correlation times the standard deviation multiplied. So whenever the correlation equal to 0, then the expectation of x and y equal to the multiplication of the expectation. That's also a very common property between independent variables. All right, and then we also mentioned that the least square regression line, whenever there's random points, random pairs of number between x and y, we often draw them on the plot. We draw each pair x, y, we draw a point. If you have many pairs, you end up having a scatter plot, because you got scattered bunch of point on the XY plane. And one of the study we often do is determine, does the variable x and y have any linear relation in there? So we want to determine a line. This line often definitely have one single point. That will be the point represented by mean x, mean y. The mean value for x, mean value for y as xy pair. That point will always be on this line, the linear relation between x and y, that we have a point. The thing is, we don't know what will be appropriate slope for the line. So we know there's definitely a point that will always be on the line, but then we don't know the proper slope. So instead we try to devise or construct a line that will be the best line to determine the relation between them. So that's what we did. We assume you have a to be determined slope, and the line will have that format. Now, the relation between this line and also any point that you might have, for example, x0, y0, from the point to the line, you can determine the distance, which is by finding the y value minus the y value of the y value of the line. Subtract them, and that distance we wish to make it as small as possible, so we can find the expectation of the deviation from the y value to the y value on the line. The deviation we want it to be as small as possible. So how do I do that? We can make a minimum value calculation. This is a degree 2 function of the b. B will be the slope of the line. That's called the function kb. So we find the derivative of kb and make the derivative equal to 0. That way, we will be able to find the value for b that will offer the lowest value from that expectation summation squares. So this line is called a least square because we wish to have the minimum possible of the square deviation. All right, so we got that formula, the formula for the b. B equal to the least square line, b equal to correlation time the standard deviation of y divided by standard deviation of x. Y is a dependent variable, x is the independent variable. So then the derivation of it is a calculus process. If you are interested, you can read the whole process. It's a degree 2 function of b, so degree 2 function is a parabola. So you have to do is making the derivative equal to 0 to find the critical point. And at the critical point, we achieve the minimum value of the function kb. So that's the formula for b. And it's something that might be useful later if you need to just try to write out your equation of the line. So that's that. And this example, I think we went through this, try to devise the correlation. I think we did most of this example. Any question? So this is a correlation calculation question. And we can also calculate those example 5 of section 4.4. So that question, we actually went ahead and find the regression line of that one. Example 5 of 4.4, which way when the lesson should copy that, it's this one. Okay, so this is the first example that we did was a discrete case. This is a continuous case. So for this continuous case, we wish to kind of follow the steps on how we determine equation of the regression correlation. Let's try. So the original question was like this. We're given the joint distribution function. This example 5, it has a uniform distribution on triangular integration region. And before, when we were studying 4.4, we know where the marginal distribution of it. We find the marginal distribution for x and for y. With this, we can find the expectation of it. This is the expectation for x equal to 1/2, for y equal to 1. Maybe we can go from the beginning. So let's see. This is the integration, the definition for the density function. X is between 0 and 1. Y is less than x plus 1. Y equal to x plus 1 is this. So it's below that. Y is below that. This is the y equal to x. All right. So did we actually go through this one? I feel like maybe we did.
Yeah, because when we stopped at the example on the slide.
Let's see. We didn't do this one. Yeah, it looks like it's completely new. So let's go through this. Like, let's try to find out the correlation and also find a regression equation. So in this equation, it has this, like x equal to x is between 0 and 1. However, the y value, y is lower boundary is x, so y equal to x is this line, right? And then y equal to x plus 1 is this line. They're parallel, right? So then the integration region is right between these two. So that's how it looks like. So then let's see, if we wanted to find the expectation for x, I mean, in the spirit of trying to find the covariance between x and y, we will need to find expectation of x times y minus expectation of x and then expectation of y. So I'm gonna try to find all three. In order to make it easy to calculate, we'll just follow the same as it was being defined. So we need to integrate. So we need to find a proper integration order. Here, it's already have the x in numerical boundary, and the y is in variable boundary. So it's easy to integrate to integration of dy dx. So we would do dy dx. The x is 0 to 1, as you can see. And the y will be x to the plus 1. Sometimes the definition itself is a good indication of what order will be. We should do x times y because I'm calculating expectation of x. I should use capital X on the set equation. Because it was really there. Multiplied by the density. The density is 1, so that means we don't have to do anything there. So that will be the first calculation. Are we okay? As long as you calculate expectation, you can follow the same so that we don't have to lose the consistency of the equation. For example, if you're calculating e of x, you'll be integrating the x times the density, but the density is 1, so it's just x. And then you can still do dy dx. Our expectation is integrate over the entire domain, entire domain of density, so 0 to 1, and then the lower boundary is still x, upper boundary is x plus 1. So that's how we find e of x, expectation of x, and we do the same for expectation of y. Again, it should be positive y. Okay, switching the positive and lowercase y. And it's still going to be the same integration limit, 0 to 1, x to x plus 1. This time we're integrating y times the density with 1, so just y then. And then dy dx, the same integration order. So once you find the proper integration limit, you can reuse it as long as you're doing double integral. Are we okay? If you prefer to use it single integral, you have to find the marginal distribution for x and y. So to me, that's a lot of work. Especially if you want to find, I think, if you want to find maybe the
You have to change boundaries.
right, you have to
So you have numerical boundaries for.
right. So it will be, so to me, as far as the expectation, we can reuse the same integration limit. So let's finish the calculation part. The first one has two variables. So this one is y dy, and you can integrate y dy. It will be y squared over 2, but x is multiplied. So x times y squared over 2. Integration limit will have x and x plus 1. That's the inner layer of the integration. On the outside, you still have to do 0 to 1 dx. X has a boundary. So finish the integration. We put in x plus 1 for the y. because the inside would dy, so it would be x over 2. And then is x plus 1 squared minus x squared. So that's the whole substitution process. And then we have to do the x. Are we okay? So on the inside, if you simplify the x squared minus x squared, it goes away. If you simplify, it's just 2x plus 1. And then 2x plus 1 times x over 2. So the integration is 0 to 1. And then x times x is x squared. Then the 1/2 times 2 is 1. 1/2. And then there's an x over 2 times dx. Right, and then we finish the integration of this will be x cubed over 3 plus x squared over 4. And we put in 0 and 1. When there's 0, they're all 0. When there's 1, is 1/3 plus 1/4. That's 7 over 12. So expectation of x times y is 7 over 12. Are we okay? The integration part takes time, so I wish we will all pick our pen and double check our calculation. At least that's what I think the expectation is. Are we getting the same answer? Right. You can definitely confirm with the book there's a solution. So second calculation, let's integrate. Integration of the inside is x dy, but it's a dy. So for y, the antiderivative will just be a y, and then upper limit, lower limit x plus 1 minus x is 1. So that would just be 0 to 1 x times 1 dx. So integrate. Inner layer is what we have now. And then integrate this function, you have x squared over 2 as the antiderivative. We put in the integration limit 0 and 1. The final answer is 1/2. So expectation for x is 1/2. And it makes sense. I mean, x is from 0 to 1. Even though you see a parallelogram, but then the whole density on the x part is consistent. So the mean value for x should be 1/2, right? X doesn't get any thicker in the whole thing. But y value is different. Y, you can see it's less on the bottom, but there's more in the middle. But it could also be 1/2 of y value. Since it does have some kind of symmetry on y value. Let's see what happens for mean value for y. We'll integrate y dy. It will be 0 to 1. The inner layer is y dy integration to y squared over 2. Going to put in integration limit x plus 1, and then dx. So the antiderivative would be 0 to 1, 1/2, and then x plus 1 squared minus x squared, which should be 2x plus 1. And then dx. Right, this integrated times it's 1/2 times 2x is x. Antiderivative for x is x squared over 2. And then 1/2 times 1 is 1/2. 1/2 antiderivative is 1/2 x. Right, and then we evaluate this 0 to 1. And plug in 1, we have 1. So the mean value for y would be, this is 1, right? Right in the middle, it's 1. There we have it. Any question? So now we have the mean for x times y is 7 over 2. Mean for x is 1/2. Mean for y is 1. So covariance for x times y, which equals 7 over 12 minus 1/2 times 1 is 1 over 12. That's covariance. Any question? All right, more. We also have to find the variance in order to find standard deviation, in order to find a correlation. So there's one calculation. Right, first we'll have to find expectation of x squared. We do the same, maybe this is a bit tedious since we have to do double integral. If we find the marginal density for x, maybe we can make a single integration. But anyway, 0 to 1, I'm doing the same double integration x to x plus 1. At least the calculation formula will be the same. And then we have x squared times 1, and then it will be dy dx again. So that will allow me to find the covariance for x. This will be 0 to 1. This is the dy, which will be 1. So there's x squared factored outside. The dy part is upper limit minus lower limit is 1. And then we have the x. The antiderivative will be x cubed over 3. Plug in 0, 1. This is 1/3. That's the expectation of x squared. That means the variance for x is expectation of x squared minus the square of the expectation, which is 1/3 minus 1/2 square. That's 1/3 is 4/12. 1/4 is 3/12. This is 1/12. Okay. Are you okay? Same thing, we can find expectation of y squared. In order to find the variance for y and therefore find the standard deviation for y, expectation of y squared equal to the same thing, 0 to 1, same double integral, the joint distribution. And then there's y squared dy. And then dx. Now, the inner layer of the integration have the antiderivative that's y cubed over 3. I have to put in the integration limit x and x plus 1 dx. Right, this is a cube power. It's a little harder to find the differences. It will be 1/3, and then y. It's not y. It's x plus 1 is y. So it's x plus 1 cubed minus x cubed. Right, and then we have to dx. So this we can use the power rule to find the antiderivative. According to the power rule, 1/3, and this is x plus 1 to the power 4/4. That's the antiderivative of this one. The antiderivative of this one will be x to the power 4/4. Okay, and then we put in 0 and 1. Okay, so then what we see is, what is it? We put in the 1, it will be 1/3 to the power 4. 16. 16/4 is 4. So it's 4 minus 4 minus 1/4 at the upper limit. Lower limit, it will be putting in 0. So 0 down is 1/4. Right, so this one is longer. What is this? This is a 1/3. 16 minus 15 over 4. So this will end up being 14/12, right? Which then make it 7/6 for the expectation. Are we okay? So then the variance for y, as we write it, it gets longer and longer. Let's try to keep track of what we're doing. The variance for y is expectation y squared minus the square of the expectation. This is going to be 7/6 minus expectation. Expectation of y, we get 1. So 7/6 minus 1 squared. which will be 1/6. That's the variance. Okay, so now we're ready for a calculation of correlation. The correlation will be this is notation. Correlation equal to covariance of x times y, f of f and y, divided by root of their variance of x and variance for y. Okay, the numerator we already find the covariance, it was 1/12. So numerator is 1/12. Denominator is root of what's their variance? This variance is 1/12. This variance is 1/6, right? 12. 6. Wait, okay. And then what is this exactly? 1/12 over root of 1/12 is root of 1. So we have root of 1/12 divided by root of 1/6, which is root of 1/2, which will be root 2/2. So that's their correlation. So they kind of have a positive correlation. Any question? We already have this. I'm just trying to review the process to see how it is. There we have it. The covariance in the textbook, covariance between the two variables is 1/12. So the correlation is 1/12 divided by root of 1/12 times 1/6, which is root 2/2. And then the least square regression, it goes like this. It's supposed to be y minus the mean value of y equal to the b times x minus the mean for x, right? It was like this. And we got a formula for the b. I'm trying to write it in a way that's more easy to follow. The b equal to correlation times the standard deviation for y divided by standard deviation for x. Now the correlation we just find out it was root 2/2. Standard deviation for y, I remember it was root of 1/6. Then standard deviation for x is root of 1/12, right? So we flip it upside down. This will be root 2/2, and then these two, that one's bigger. So what is this? The 1/6. This also have 1/6. You cancel the 1/6, it's like 1/, you go 1/2 there. And this is already root of 1/2. They still cancel. It's actually equal to 1. Oh, okay. So the coefficient that equal to 1, if I'm right. Okay, and then we had this one is mean for y, it was 1. This one is mean for x is 0.5. So basically it's 1 minus 1 equal to x minus 0.5, or y equal to x plus 0.5 if we try to determine the regression line. Are we okay? But in the text is already follow that kind of. So this is an example using the correlation to identify the least the regression line, the following regression line. Any question? Right. So this is a homework. If we try to supplement a little bit of the textbook exercise with a Weber question, so we kind of have a little bit of both sides. In the textbook, we tend to have the relation function in a formula, but on Weber, we tend to have a table. We do have a few formula about the continuous case, but most of the discrete case are given by tables. So then we try to cover all the different scenarios. All right, let's move on to 4.3. The title for 4.3 is conditional distribution. So pretty much we're trying to look at relation now. Now, what's the conditional distribution does? We will have to find out conditional probability. So with conditional probability, you have one that's like among the two variables. One is given first, and we look at the impact of the other variable. So it's different than the covariance. Covariance is not looking at order. Covariance is symmetrical concept. Like your relation with me is the same as my relation with you. So one way or the other, it's the same, but condition is condition of the other variable being determined first. And we look at the distribution of the second variable. Now, the conditional distribution will be defined for the discrete case and the continuous case. Both of them follow the same idea as how we interpret conditional probability. So here, suppose we have a joint distribution, which is probability of A and B is probability X equal to X, Y equal to Y. But the joint density or joint distribution can be considered as probability of a joint event. So if you want to find the single probability or the single variable, which will be kind of like the marginal distribution function. So if you divide the joint density by the marginal density, that is the conditional probability of A conditional on B. So that gives us the definition for the conditional distribution. That's joint distribution divided by the marginal distribution. That's our conditional distribution. And but often the conditional distribution are given a certain value. For example, if you look at the bottom definition, the joint distribution is fxy divided by fyy. So fxy has variable x and y, the denominator has variable y. So as a result, the whole division has x and y. So the conditional distribution of one variable condition on the other one does not reduce number of variables. So unlike the marginal distribution, if you reduce number of variable onto only x, then you have marginal distribution of x or marginal distribution of y. There's only one variable. But in the conditional distribution, even though we condition on one variable, we still have two variables. Unless one of the variables like b, you have like y equal to 5, and then the y all become number. Then this will be a variable. The variable would only be the x variable. So depending on the scenario, the question often changes. A two variable function or a one variable function, it depends on whether the variable is given or is fixed. All right. So our conditional distribution or conditional mass function is being defined as the joint distribution divided by the marginal distribution. The conditional can be x or y. So the first definition is the conditional distribution of x given y, that is fxy divided by fyy. Conditional probability mass function of y given x is denominator will be the fx if x is a condition. Or any question? Conditional distribution have its own importance. Just say conditional probability allow us to study some special things that are happening when one of the factor is being fixed. All right, so let's talk about conditional expectation. With conditional probability, we have conditional expectation. How do we calculate conditional expectation? You are using the conditional probability as a probability value. So probability value multiplied by the variable value would allows you to find out the conditional expectation. So with conditional expectation, we have conditional square of the variable. Therefore, we have conditional variance. So basically, the conditional variance is expectation that the variable y minus e of conditional y given x if the x is given. So basically, we're treating the conditional probability as a probability distribution in itself. And then from that distribution, we can calculate variance or expectation. Any question? So 4.3 tend to be difficult because for the continuous case and discrete case, we have different scenarios. Let's see. Let's look at some example. We start with discrete example. I'm going to move on to the continuous example. Out here, we can see that in the text, we have all the function being given in formula. So your the result will also be formula, even though they're actually just two number or four or six number. Now the joint density goes x plus y over 21. X takes on 1, 2, 3. Y takes on 1, 2. Meaning that 3 times 2, there's only 6 number in this distribution formula. And if you wanted to find the marginal distribution for x, Okay, and then that's done in the past. But in the book, it was given by a formula, x equal to 1, 2, 3. So you got 3 number for the distribution of x. Now, y value, the marginal distribution for y equal to 1 and 2, those are marginal distribution given in a formula format. And here we have the conditional distribution also is given by a formula. So basically, you take the joint distribution, the fxy, divided by the marginal distribution, you divide it and cancel the common factor. There you have. But because of the disgrace case, it's not as visually easy to understand compared to the number sense, have it in the number form. Okay, so let's try to make it easier to see how it's related. This thing, when we were studying, I tried to draw them in a picture, so it's actually it makes a lot more sense number wise. So here we are. So before what I did was just looking at different x value, y value, what will happen with the distribution. What I did in the past was like 1, 2, and then 3, and then the y value takes on 1 and 2. So for x equal to 1, y equal to 1, 1 plus 1 equal to 2. So then this is a 2 over 21. And now it's 3 over 21, and then 4 over 21. And this is 2 plus, right, 3 over 21. 4 over 21. These are the joint distribution when x and y both are considered. Okay, and then it's easy to tell that we add up all the rules to get distribution from y. You add it together, it's 12 over 21 for the probability of y equal to 2. And this is 9 over 21. So we'll be repeating what we did earlier. This will be 5 over 21, 7 over 20. And these are the marginal distribution. And this is 9 over 20. Okay, so these are still what we had in the past. So what will happen for the conditional distribution? For example, you can conditional on the fact that for example x conditional y. So this is, say we calculate conditional on y conditional on x. So what you have to do, you're gonna take the joint distribution divided by the marginal distribution of fxx. That's how you can create a distribution for conditional distribution of y given x. That means all these are going to be in the denominator of all these. So that really changes how it looks like. For example, this gonna divide by this. So then the first one is 3 over 5. So we did instead of 3 over 21, 3 over 21 divided by 5 over 21. This is 3 over 5. This is after you know that x equals 1. And then 2 over 21 divided by 5. This is 2 over 5. Okay, this one is going to be 4 divided by 7. So it's 4 over 7. And then 3 over 7. Conditional on x. And this is going to be 5 over 9. And 4 over 9. Oh, okay. So that was the formula. What would be the formula? This is that one. The formula we're given is x given y. I did it y given x. Now, what if we want to given y given x? Let's try to look at it. So if we calculate g x given y, we'll do the joint distribution divided by the marginal distribution of y. So every single of these number will be divided by their distribution on the y. So for example, the first one will be 3 divided by 12. And 4 divided by 12. And then 5 divided by 12. So then everything here are changing. You still have 6 number. Are we okay? So for every x, every y, you still have it. And this is going to be 2 over 9. Because that one, the total is 9. And then 3 over 9. And 4 over 9. And I kind of agree with this formula. It goes 3y plus 6, x plus y in the numerator. So numerator stay the same. So the numerator was like the top one was 3, 4, 5, and then 2, 3, 4. Numerator stay the same. The denominator change to the corresponding numerator on this, right? And then that's what happened. The numerator is x plus y, just like the numerator in the original distribution, but the denominator becomes 3y plus 6, just like the fyy is equal to 6. Are we okay? So you can see in the conditional distribution, we're still maintaining the structure of having all 6 number, but then each one number are being changed due to the fact that we have to do this factor division. And I'm just gonna explain that a little bit. So you see, this is all illustrated. On the top is the joint distribution and the marginal distribution. On the bottom over here is the distribution of x given y. So you're dividing by this total is all in the denominator. Over here is conditional probability of y given x. So those distribution at the margin, at the bottom margin, are being divided by every single number. So we see those. Any question? So that's the discrete case. I feel like having a table ready kind of explain a lot better than the formula stuff. Anyway. Let's look at the conditional mean and conditional variance. For example, let's say conditional mu y given 3 is saying that the expectation of y, suppose x equals 3, it will not be the same as expectation of y by itself, because knowing x equals 3 will slightly adjust your expectation. Computation wise, you're calculating the y value multiplied by each one of these distributions. Now we will need the distribution for every y value given the x equals 3. So what we need to do is y value times the distribution of the y. So we would be looking at x equals 3, right? X equals 3 is this rule. And there's 2 y values. So what you did is this 2 times the 5 over 9. This 1 times the 4 over 9, because we're conditional on the fact that x equals to 3. Are we okay? So with this, the expectations of the y value, the y only have 2 values, so you are having a summation of 2 value, but you only are using the third column here. It kind of changes our final answer. The answer is 14 over 9. Now, let's say if we want to find the variance, it will be the same. You will assume that the distribution for the y will have these 2. So we would be doing 5 over 9 and 4 over 9 as our probability value. And then you're going to take your y minus 1 over 9. For example, 1 minus 14 over 9 squared times for the 1, right? And 4 over 9. And then 2 minus 14 over 9 squared times 5 over 9. That's the 2 numbers. Well, that's already there. The total calculation will be 20 over 81. That's the calculation for the variance of y. Any question? It's conditional on the x equals 3. That's a conditional mean and conditional variance. You can see it's slightly different than the calculation for mean and variance by itself, because we're using the distribution. That's different. Originally, your calculation for mean y or sigma y, you'll be using this, like 12 over 21, 9 over 21. for the calculation of mean and variance. Okay, so we're using a different set of probability value in the calculation of mean and variance compared to the conventional one with the original, with the non-conventional. Okay, so let's look at the relation of the conditional means. The conditional mean of x given y should be a function of y because if you're calculating the mean of the x, you are averaging the x value, but assuming that you're averaging the x value based on the y value. So if the mean is calculated over the x is out of the problem because you're averaging it out. But since y is still a variable, this will be a function of y. On the other hand, the conditional mean of y given x will also be a function of x. So sometimes we do wish to know the relation of the two. So if the expectation of y given x value is a function of x, we might want to find out that function. Now, suppose it is a linear function. And suppose y given x is a plus bx, we might want to find out the number a and the number b. And that kind of goes back to our linear regression line formula. And we see that it's the a and b has already been determined in the previous section of our linear regression. So how we find it out? The process is a similar process, so kind of optimization process. So, so now number one is expectation of y given x can be calculated by the y value multiplied by the distribution of y given x. Since it's a conditional expectation, so we use conditional probability. And the conditional distribution is a joint distribution divided by the marginal distribution. Assuming this equal to a plus bx, we multiply both sides of the equation. I mean, our ultimate goal is let's find out the formula for a and formula for b. So we multiply both sides of the equation with marginal distribution f x y. Now, if you do this, then the this side of the equation you have multiplied the denominator to get rid of the division. So then this is our equation. The left side of the equation, there's no more division. On the right side of the equation, if we multiply the marginal distribution fxx, it will have something actual. So we're treating this as an equation, left side and right side. And we multiply both sides of the equation by the marginal distribution. We have this. Are we okay? We're trying to devise some kind of formula. Now, if you take a summation of both sides of the equation with respect to the x variable, then you have this. So from this, now summation goes out of the equation. Now we have this. And then the this side, the x f of x, you bring the b out. Summation x f of x is expectation of x. That's the mu x. On the other side, the a in time f of x summation. Summation of f of x is a distribution. Summation of f of x equal to 1, right? So this summation on the right side is a plus b times mean of the x value. On the left side of the equation, it's a double integral where it's over the y times the density. That's the expectation of y. So which is basically saying mean y equal to a plus b times mean x. And that is saying that in this function of a plus bx, the point mu x mu y will have to be on that equation of line. It's on the line. So this just to verify that mu x mu y is a special point on this line. I'm trying to find out. Any question? So now we have a special point, and then of course all we have to do is maybe find out the the point itself kind of indicated a point. Maybe if you find a slope and a point slope formula allows you to write out the equation of the line. Now, next thing is now that we have this equation, what we're going to do is we multiply both sides of the equation by x. So this equation, you multiply by x, this side you multiply by x. If you multiply the right side of the equation by x, left side of the equation by x, that's the expectation. That's the expectation of x times y. If you multiply the right side with x, this is move the 8 out of the summation, x as the x summation is e of x. Now, x squared of x is e of x squared, so then we have that relation, which in this side is expectation of x times y, according to what we did in last section. E of x y equal to x mu y plus correlation sigma x sigma y. On the right side of the equation, we already have that. Expectation of x squared equal to the variance square, the variance plus the mean of x, because variance is equal to sigma x squared is equal to expectation of x squared minus the mu x squared. So then expectation of x squared would equal to sigma x squared plus mu x squared. So this is an essential part of the definition of variance. So this one equal to this one. All right, you can look at both sides of the equation. They have common term. Any common term, we can get rid of it. Ultimately, we're trying to find out formula for both. What do we have? So we're going to combine this equation with this equation, the mu y equal to a plus bx. Okay, so these two combined, you have a formula for the b. B is the same formula that we were talking about, the linear regression line slope. The slope b is the same, and the a is really pretty much from the Poisson formula, the y-intercept. I kind of devices all here says what's the solution of equation, this equation, and this equation together will give us this. So I was like, how do we get those two combined? So we did this. This is a equation, this is the equation in the previous page. Now we substitute mu y in here, and then we get this. And then we now have some common term on both sides of the equation that we can cancel. Cancel a times mu x, we have this. And then this one and this one, again, we can cancel common term, and we have this, which allows us to get b. Once we have the b, we plug in the b into the second equation, which then gives this. So then pretty much that's all the process, like simplifying the equation. And so ultimately, overall, the answer is that now we already have the formula. The expectation y given x is if it's a linear, that's a linear equation is mu y plus the b times x minus mu x, right? And that's it's pretty much the regression, the linear regression line with x is given. So there's some subtle connection between this section and the last section. Any question? All right, so let's try to look at the meaning, the implication of it. We mentioned before expectation of y given x equal to 1 can be calculated using those two. These are actually the column in that page with x value, x equal to 1, x equal to 2, x equal to 2. You have 3 column conditional distribution for x. So then this mean value can be calculated using that column. Now, mean, if x equal to 2, the mean value for y is using a different column, different set of the distribution. And this is x equal to 3, expectation of y. See, they're not the same. However, if you take these 3 and conditional on the distribution of x again, so x, the overall marginal distribution for x is x equal to 1, 2, 3, have those probability. And then we multiply these, we get 33 over 21, which equal to the same expectation of the y value. Right, so what do we want to get from here is in an actual example setting, numerical setting, we find out the mean of the conditional mean is the mean of the variable. I wonder if that makes sense. This is what we're getting, that it's called the law of total probability for expectations. So as we see, the expectation of y equal to 33 over 21. That's the overall expectation of y. based on the earlier page, expectation of the expectation of y given x also equals 33/1. So the mean value of the conditional expectation or expectation of the conditional expectation equal to the overall expectation. It's called total probability of the for expectation. Basically it says suppose x and y are a random variable that has a discrete type, and suppose e of y exists, then e of y equal to the expectation of the conditional expectation. Any question? So I would say the second layer of the expectation, the inner layer of the expectation, like we said, it will be a function of x. But the outside, if you want to find that if that was a variable, the variable part is in the x, right? This variable part, the expectation already get rid of the variable part of x. So then the second expectation has to use a distribution of x itself. So this, you use distribution of the y given x, but this you use a distribution of x itself. It's a double layer integration, which cancels any randomness in the distribution. So basically, we're calculating mean value for y. That's my understanding of it. So this one, other than they're equal, it doesn't really provide a lot of other kind of things. What's more important is the second one. That was a mathematical proof of it. It's like 2-layer of expectation, 2-layer of summation. If we are looking at a discrete case, if you want to prove it in the continuous case, you have to do it double integration. Now, it's very important for the law of total probability for variance. So the first one is the law of total probability for expectation. And this one is called law of total probability for variances. What it does is saying that the expectation of conditional variance plus the variance of the conditional expectations, kind of tongue twisting. They added together, which equal to the total variance of the variable y. So here is variance, expectation of variance plus variance of the expectation altogether equal to the variance itself. Any question? This can be proved. Here we have a mathematical proof of this. Okay, so how we prove it? Basically, we're going to try to devise a formula for both of these two. A mathematical proof we often enter from the longer side or more complicated side, try to find ways to combine them to eventually lead us to the other side equation. So if we ever want to prove it, we often go by the left side of the equation. There's two of them. So what we want to find, we want to find a formula for the expectation of the conditional variance, and then we want to find a formula for the variance of the conditional expectation. And among these two, we wish to find maybe some of their terms are overlapping, or some of them are opposite signs. So then maybe we end up combining them, which is the case now. Calculation of the expectation of conditional variance. You see, how do we calculate variance? Variance equal to expectation of the square minus the square of the expectation, right? So then this, the inner layer of that is by definition of variance, or a common calculation formula for the variance. And now we're going to look at moving in the expectation. This E, this expectation of a subtraction. So we expectation of subtraction is E of the first one minus E of the second one, right? So first you expand the variance definition, then you move in the E of E this, E of E this. However, these two are not the same. The first one is expectation of the conditional expectation. Based on what we learned last page, E and E will kind of cancel the randomness. That's really the total probability for expectation. This is basically expectation, right? There's no more condition. Like if you have 2-layer expectation, you get rid of that condition. You're just calculating expectation. However, this one is different. This is expectation. The square stopped there. So this E does not combine with that E because it's got a square first. And then E, so this is the E of the square. So that one kind of stays because it's difficult to get it calculated. Now let's move on to the variance of the conditional expectation. Now we're gonna go by the definition for the variance. Definition for the variance of a variable will be variance expectation of the square minus the square of the expectation. we will look at the route. So the first one is you have to square and then take the expectation. This one, you're gonna take the expectation and then square. Now, E of the E, apply the total probability for expectation. It cancels out the randomness of the variable, which equal to E of Y. Are we okay? So that equal to this, and this one, you see, it doesn't go away, it will stay. But the good thing is after we expand it, we realize this one is the same as that one. They kind of cancel each other out if we add it, right? If we add this one with this one, that one and that one, it's that negative, this positive cancel, then you have expectation of y squared minus expectation of y squared, square of the expectation, which then is equal to the variance of y. So after we expand it and then add it, after add it together, we realize it does equal the variance of y. Any question? So it's a very abstract proof of it. It doesn't have integration. All it does is really applying what we just proved. The expectation of the conditional expectation cancels out the conditional part. All right. So what's the benefit of knowing this? Because sometimes the expectation of the variance or the variance of the conditional expectation are easier to get than the total variance. Which kind of like this example. X is a Poisson distribution with mean 4. Y is a random variable whose conditional distribution, given that x equal to x is a binomial distribution with sample size n equal to x plus 1. So the y is a binomial distribution, but the sample size depends on the x. And the probability is constant equal to the number p. So in this case, if we want to find the variance for y, it will be kind of difficult because y is not a standalone distribution. Y depends on the x variable, right? So in this case, we have a lot of information about the conditional behavior of y. It doesn't have a distribution or a property of y on itself. So if we want to find variance for y, we actually have to look at the conditional distribution. Now, based on the fact that y is a conditional binomial distribution, so the expectation of y given x is n times p, n equal to x plus 1, so x plus 1 times p. Okay, so that is the expectation of y given x. On the other hand, expectation of the conditional expectation will equal to e of y. So and that means that E of y given x is E of x plus 1 p, and then the p is a constant number, bring the p out, E of x plus 1, E of x, x is Poisson distribution with mean 4, E of x equal to 4, therefore it's 5p. So E of y actually is given. So we now using all this property that we learned, we realize we now have the mean value for y, and we're gonna move forward, try to find the variance for y. So how do we do it? First, we can find the conditional variance for y given x because the y is a binomial distribution. The variance of the y will equal to np cubed. So n equal to x plus 1, p and q is 1 minus p. So that is the conditional variance. So what is the variance itself? Variance equal to variance of the conditional expectation plus expectation of the conditional variance. All right, so the conditional expectation, we already know that equal to x plus 1 times p. So variance of this will be fine. And then what is the variance is the NPQ. All we have to do is take in that expectation. E of x, we already have it. That's 5 plus 1 p times p times 1 p. The first part of it, it's really variance of x plus 1 times p. The p move out of the variance calculation. You have to square the p because p is a factor. And then variance for x plus 1, the 1 has no variability. So variance for x plus 1 equal to variance of x. Now, the Poisson distribution is variance equal to the mean. So variance of x equal to 4 as well. So that was 4. And that's 5 times p times 1 minus p, and then we combine the like term, and we have the 5p minus p squared. That is the variance for y. So it turns out the actual variance and actual mean for y are both function of p. P is constant. So we're not being able to figure out, even though originally we only know the conditional behavior of the variable y. Any question? It's a special scenario, but the thing is, many times there are situations when one is closely related to the other. It's hard to separate them. So we have their conditional behavior, but we don't know how it's behavior by itself. So this is a very likely possible situation. Okay. Let's look at conditional probability and the continuous type. X and Y have a distribution. Suppose we have a joint distribution, fxy have a marginal distribution, fxx and yy. Therefore, the division will allow us to define the conditional distribution for y given x. If you want to find conditional expectation, all you have to do is write type the conditional distribution and integrate it on this domain. The conditional variance will be the conditional expectation of y minus the conditional mean squared. And same thing, you can also use the expectation, conditional expectation y squared minus the conditional mean squared. Okay, let's look at example. Okay, so this one we have the one we had earlier, which had the triangular distribution. I think we've done this one before, right? This, yeah, we might have. Yeah, we might have done it before. So in the past we have this. Okay, this is what we have already when we were studying the conditional. We were studying 4.4. We went over this example. So now, if we want to find the conditional distribution, let's say H, which is a conditional distribution of y given x. Now the computation will be the joint distribution of xy divided by the marginal, that was a condition, marginal distribution of xxx. So the formula of it would look like this. It will be 2 divided by 2 times 1 minus x. It was this one that we need. And they should satisfy the same condition. I think it's 0 less than x less than y. Any question? Because we did that division, we still have those variables in there, so it should be the variable should be both x and y. That's the distribution. Now, for example, if we were to find the conditional expectation of y given x, it will be an integration question. You integrate y times, it will be integration of y times h y given x. It should be a double integral. Given x, x is a variable, so we integrate over y. So this is essentially a application of a single variable, so we actually do y. So whenever we do that, we still have to identify the proper integration boundary. In this case, it will be dimension is the expectation of y given x should be a function of x. So the x is still going to be the variable. So then this calculation will end up giving us instead of a number, this expectation, it is actually a function of x. Okay, let's see. So let's look at given an x value, what will be the proper boundary for y? This is our original definition of the triangular integration region. So we have x between 0 and 1. And then this line that goes y for x. Y is above this line. Y is bigger than x. So y is above this line. So the integration region is this is our integration figure. So when we're integrating for any given x value, given a x, try to find the proper boundary for the y value. So the integration boundary is lower limit to the upper limit. Upper limit is one. Lower limit is on this line, and we need to find the boundary for the y value. This is a y equal to x, so the boundary for the y value is the x. So we integrate from x to 1. Are we okay? So it's not very easy to me, it's not that straightforward, so I have to look at the eventual exercise. So the x to 1, y times the 2 could cancel, y times 1 over 1 minus x dy. So that will be the integration part. And then you see we're doing dy, so that the x will be a coefficient. We bring the 1 over 1 minus x to the outside and integrate the y dy. Y dy integrated into y squared over 2. And then there's x equal to y equal to 1 and x for the y value. And finally, we're going to use the 1 and x replace the y squared, replace the y, so it's 1 over 1 minus x. And then 1 over 2 minus x squared over 2. And then we simplify this into 1 over 1 minus x. The numerator is 1 minus x squared. The denominator is 2. 1 minus x squared divided by 1 minus x squared equals 1 plus x times 1 minus x. So the 1 minus x cancel. The answer is 1 plus x over 2. And of course, x is between 0 and 1 as a natural boundary. So that will be the conditional expectation of y given x. In this example, we did say it's a linear. So like a times bx kind of thing, right? 1 plus x over 2. It is linear. Any question? Okay, so that's our conditional expectation. If we carry out the calculation, it looks like we're out of time. I think similar process can be done for x given y and conditional expectation of y given x. Either variable, it's a symmetrical kind of relation, but the process, it depends. We actually look at the integration rate. We okay? All right, that's it for today. Do you guys finish the projects? You had time to submit? Okay.
Is it due this week?
No, I didn't really set up to do that. I'm hoping you guys finish before next month. No, we'll talk about our overall what was the answer.
Okay.
So if we agree on what should be appropriate distribution, we'll move on to calculate it.
Okay.
That's it for today. Thank you.
What?
It's up to your list.
No. Oh, we have that right now.
No,